Welcome back to ECE 442-542. Hopefully we'll get through a fair amount of material today based on the goals. But homework number 5 is not available, but it has a due date. How do you like that? So hopefully we'll have homework number 5 created for you to start looking at. And some of the material that we will talk about today should be appropriate for solving some of those problems. And exam number 3 is on the 12th of April. Relative to what we want to cover, we want to continue with our performance specifications. We haven't yet talked about the formulas for the time to peak, which are listed here, and we'll go over those a little bit more when we get into that part of today's class. We'll go through an example or two with time to peak to show what kind of fixed shapes we're dealing with. Remember, now that we're in the z-plane, our shapes have changed. Now we have circles, hearts, and wedges. Wedges are the time to peak we haven't yet covered. So we'll have to talk about the wedges today. We'll do a summary of those performance specifications, and those are again based on a two-pole. That's just to give us an idea or a feel for where we might want our dominant poles located in the z-plane. We'll finish with a constraint table that you can then look up or use to try to infer how you're going to make these formulas work to your advantage when you're given certain performance specifications. We'll use that to then design a transfer function, a desirable transfer function that we might want to make our closed-loop system look like. We'll show how we can simulate that in MATLAB. We'll maybe look at some grid lines in the z-plane. Now the grid lines are a little bit more interesting. They have the logarithmic spirals. They have the natural frequency lines, etc., and we can make those look the way that we want, and we'll try to illustrate how that can be done. Then we will relate what we've been talking about in the past with sampling frequency to the Nyquist frequency and what that might mean relative to aliasing. And you've maybe already seen that, but now why are we always using this rule of thumb of 30? And how does that maybe relate to this Nyquist frequency? And we might go through an example that our performance specifications, we might have settling time specs, peak time specs, and percent overshoot specs, and they may not all be consistent, meaning we may not be able to, on the first attempt, satisfy all of those specs with one particular pole location. So now we have to figure out which one do we start adjusting. Do we start adjusting the heart? Do we start adjusting the circle? Do we start adjusting the wedge in our z-plane to try to satisfy all of the different performance specifications? And then, which we probably will not get to, but we'll start talking about controller design or provide an overview of controller design, which is where we want to get to in this half of the semester. In terms of performance specifications, we talked about settling time, which were circles. We talked, and that was number 1. Number 2 was percent overshoot. That was logarithmic spirals, or what we were generously calling hearts, just to give us something to think about in terms of shapes. And now what we want to do is look at what these time to peak lines or shapes look like in the z-plane when we map them from the s-plane, which time to peak is pi over omega sub d. Omega sub d is the distance of our poles from the horizontal real axis. And I've illustrated one in green and one in blue, and they are given by damped frequencies of omega sub d1 and omega sub d2. And relative to that, how do those map, or what's the mapping that we use to go from the s-plane to the z-plane? What is our relationship between s and z? And that's what I want to indicate in red with this mapped arrow. Z equals east, west, north, or east, right? E to the st. So it's E raised to the st, where t is our sample period and s is our complex frequency variable. If we now have an s equal to j omega sub d, what's that going to do with our mapping? Or what does that look like in terms of where that ends up? Do you remember? If I plug in a pole, let's say I have a pole here, or I have another pole here, maybe I should give them the same real part so that you understand that it's not the real part that's making the difference. And those are supposed to be maybe on those lines. But now if I had a pole with a damped frequency of j omega sub d, then if I map that, and maybe I should just do it with zero real, well, it doesn't really matter. What's going to happen if I now plug in e to the j omega sub dt? What does that look like? In green, I now have e to the j omega sub d1 t. And if you remember, we were actually just collecting omega sub d times t into an angle, e to the j theta sub d. So this natural, or this damped frequency is now corresponding to a line. If I looked at every possible real value on this dashed location, I would just be getting something at an angle of j theta sub d, another j theta sub d, another j theta sub d. Hopefully it's clear that now I'm looking at an angle or a wedge, and this is now at an angle of theta sub d. Let me call it theta sub d1 to be consistent with the omega sub d1. Similarly, if I now looked at any particular pole on that horizontal blue dashed line, now I have e to the j omega sub d2 t, or this is now e to the j theta sub d2. And how is theta sub d sub 2 related to theta sub d sub 1 relative to this picture in the z-plane? Is theta sub d2, I haven't changed capital T, and all I've now changed in that expression is changed omega sub d1 to omega sub d2. And I think you see in the S-plane that omega sub d2 is a bigger value than omega sub d1. What's that mean relative to the angle? It's a bigger angle. Meaning now I have, if I mapped points that had the same angle of theta sub d sub 2, then they would be on those particular lines. Which means that now if I have a given time to peak specification, that's going to impact my angle in the z-plane. For example, suppose that I now look at an example where I might have a time to peak of 6 samples, sample periods. I'm now trying to get to my peak time and my step response in 6 samples. And I want to now find theta sub d. But how do we define theta sub d in terms of our parameters, omega sub d, sigma, and t? Hopefully we remember that theta sub d is omega sub dt, and what is omega sub dt in terms of time to peak? up above, we have omega sub d as pi over time to peak. So if we substitute pi over t sub d into theta sub d, we now have omega sub d is pi over time to peak times the sample period. But if we want our time to peak to be 6 sample periods, we can now substitute 6t into time to peak. The t's now are canceling, and I now have pi over 6 as my angle. And pi in radians translates into, we wanted that in degrees. That's now 180 degrees divided by 6. Maybe a good thing that I selected these numbers. Now I have to divide 180 by 6, or theta sub d is now 30 degrees. So now we know that if we wanted to have a peak time of 6 sample periods, we would be looking at our poles being, how do I want to say this, above or beyond that angle of 30 degrees in the z-plane, where theta sub d is the 30-degree angle, and how far away we are from the origin might be impacted by the settling time, which is our circle. And we could now intersect this angle with our radius, which gives us our settling time of a circle. Now, relative to theta sub d also actually chops up how many samples we have in an oscillating waveform. Or, said another way, theta sub d can influence the number of samples per oscillation cycle. What do I mean by that? Suppose theta sub d is 60 degrees. And remember, theta sub d is omega sub dt. If theta sub d is 60 and one oscillation cycle is 360 degrees, or 2 pi, if you think of a period of a sine wave or a cosine wave, has a period of 360 degrees or 2 pi, we now take 360 and divide by that theta sub d, and that now gives us 6 samples per oscillation cycle. And I have a question mark to remind me that this is now what I want to be thinking about. If we had an exponentially damped cosine waveform, it would have this shape. What I'm saying with a theta sub d, if our poles were producing this shape, and we had poles that were corresponding to an angle in the z-plane of 60 degrees, then we would see, in the discrete time sense, only these values where these dots are, and I apologize if these don't look uniform, but that's what I get with respect to drawing. But those would be uniformly distributed along this oscillatory shape. And if you count that, then you can see that we have 1, 2, 3, 4, 5, 6 before we start repeating that 2 pi interval or 360 degree oscillation, meaning we had a peak at 0, then our next peak is at 6, and our next peak would be at 12, etc. So that now the number of samples per oscillating cycle is determined by theta sub d, and that's now equal to 6. That's different from our rule of thumb. Our rule of thumb was what? We were saying 30 samples per our natural frequency. And so if we had a natural frequency, then we would be looking at 30 samples instead of this 6 samples that we have right now. So in this case, we can think of it either as n sub d is 360 divided by theta sub d, or we could say the number of samples times theta sub d is 360 or 2 pi. Meaning, now we could actually go the other way. Suppose that somebody wants a particular number of samples per cycle. What does that correspond to in terms of theta sub d if we wanted that in radians? Relative to this formula, we're really just solving that for theta sub d, either in terms of radians or degrees. Meaning, if we wanted so many samples per cycle, then that would force our angle theta sub d of our dominant poles. In this case, in radians, we would now have 2 pi over n sub d. Or if you wanted that angle in degrees, we would just have then this 360 degrees divided by n sub d. Or if somebody now wanted 10 samples per cycle, we now know how to produce that. We would have 2 pi divided by n sub d, or divided by 10, and 2 pi is 6.28. So now in radians, theta sub d would be this 0.628. Or in terms of degrees, that corresponds to 36 degrees. And that now tells us where this angle would be relative to our dominant poles in the, let's say, desired transfer function that we're trying to achieve or obtain. So let's look at creating dominant poles from design specifications. Suppose that we go back, and last time we talked about a particular case. Here's another case. Suppose we're given zeta, or if I say zeta, what are you thinking in terms of a step response? And you have settling time, percent overshoot, and peak time. And now if I give you zeta, you should be thinking percent overshoot. How much are we overshooting our final value? So here I could say or percent overshoot. And what shape are we thinking relative to percent overshoot in the z-plane? What shape are you seeing in the z-plane when you think of zeta, constant zeta values? Or points in the z-plane that correspond to the same percent overshoot? Settling time was circles. Percent overshoot, hearts. And time to peak, wedges, somewhere beyond some angle. Here, if we have percent overshoot, then we're thinking of hearts, so I have to do those in red. So there might be a particular zeta value, or we might have then a those are not real healthy looking hearts, but you get the idea. Which heart corresponds to a bigger zeta? The inner heart or the outer heart? Which one has a bigger zeta? If I labeled this as, let's say, zeta 1, and I labeled this one as zeta sub 2, wow. Hopefully you have better penmanship than I do. But zeta 2 is related to zeta 1 in which way? Is zeta 2 bigger or smaller than zeta 1? And how are you going to maybe do a gut check on that? What do you know relative to zeta? If zeta is equal to 0, how much damping do you have? If zeta is our damping ratio, and if that's equal to 0, if we have 0 for a damping ratio, how much damping do we have? Please answer. I'm getting busy. So you're not damping at all, are you? It's just continuing to oscillate. So zeta equals 0 is when you're shaking and you don't have any damping. And where are you in the z-plane if you're just shaking, if you're not damping? If you have no damping, where are you? Or where would you have a pure oscillation for your poles in the z-plane? In the s-plane, it's on the imaginary axis. Where does that map to in the z-plane? It maps to the unit circle. I'm giving things away, and I'm not even trying to. Is that right? I should be like Oprah, yes, the O. Oh, I get a car? Yeah, I'm not going to get a car, not from Oprah. But zeta equals 0 is the unit circle. As zeta gets to 1, then we would eventually get to having real poles along that little segment, real line segment from the origin to 1. That's zeta equal to 1. If that's the sort of the two limits, zeta equals 0 and zeta equal to 1, how are zeta 1 and zeta sub 2 related? Is zeta 2 bigger or smaller than zeta 1? It's bigger. Yes? So now if we want less overshoot, we want a bigger zeta, we're trying to squish that heart. Our heart's going to be smaller. I get accused of that a lot. I have a very small heart, especially when grades are awarded. Okay, so there's our zeta value. That's percent overshoot. And now theta sub d corresponds to what? What performance specification is theta sub d associated with? What did we just cover? This was our peak time, wasn't it? So our time to peak is theta sub d. And now we're interested in angles. Question? So the radius or circles represent settling time. That's the speed of response. These logarithmic spirals represent percent overshoot. And we could have both of those being played at the same time. We may have to look at the intersection of those. So now, suppose somebody gives you a percent overshoot and a peak time. How do we find the intersection of those? If we were sketching these, you could sketch those. You would just find the theta sub d, draw that angle. If you now had the percent overshoot, that would correspond to a zeta. You would draw the appropriate logarithmic spiral, and where those intersect is your z sub delta. If you analytically wanted to find that, then maybe we need to find a relationship between a point on this logarithmic spiral and a point on that angle, or that line. Okay? How are we going to do that? Theta sub d is omega sub dt, and omega sub d we could rewrite as omega sub n times the square root of 1 minus zeta squared, and we still have t. Or a lot of times what we will do is we will collect those two terms, omega sub n and t, and isolate this zeta factor, which is the square root of 1 minus zeta squared. We have zeta and theta sub d. We don't have omega sub n in our knowledge base or in our expression that we're trying to find for z delta, and r is related to omega sub n t and zeta. So let's now use this relationship of theta sub d, omega sub n t, and the square root of 1 minus zeta squared and solve for omega sub n t. I'm now using this equal to that to solve for omega sub nt. Or that says that I now have theta sub d divided by the square root of 1 minus zeta squared. So if I have the omega sub nt expression or variable in my equation somewhere, I can replace it with this expression that only contains theta and zeta. Theta sub d and zeta. Or what I'm really trying to get is get rid of omega sub nt in my formula for the radius, r. Because if I know the radius and the angle, then I can analytically find those pole locations. That's easier than trying to do this logarithmic spiral, unless I'm graphing it, but still graphing that logarithmic spiral can be tedious. So now r and theta is easier to graph. If that's the case, then I should have for r, that's now e to the minus, zeta is given. That was the percent overshoot, but now I'm replacing omega sub nt with this expression that's now written in terms of theta sub d and zeta. So that now, when I'm given those two unknowns, I can now rewrite that as minus zeta theta sub d over the square root of 1 minus zeta squared, and that's all this exponent on e. And now I have an equation or a formula that only contains theta and zeta. It's behaving. Put them in timeout, won't I? Yeah. So, if somebody now gives you a performance specification in percent overshoot and peak time, now you can find those poles corresponding to that by using this formula, r e to the j theta sub d, where r now is written as e to the exponent minus zeta theta sub d over the square root of 1 minus zeta squared. So let's remind ourselves what we have. Here's a summary, and I'll scroll through these fairly quickly. But settling time, you're thinking circles, right? Maybe some of you aren't even thinking. But we have settling time or circles. That's going to give us r. And we can now either be given t sub s. If we're given t sub s, then that gives us n sub s. If we have n sub s, then we can solve for r. That gives us our radius. So now we have concentric circles that depend on our settling time. Question? So omega sub d is the damped frequency. Omega sub n is the natural frequency. In the S-plane, that's the distance from the origin. And zeta is the damping ratio. So zeta is associated with the angle theta in the S-plane. And n sub s is what I'm defining to be the number of sample periods to settle. So n sub s is the number of sample periods required to reach our settling time. And so if we multiply n sub s times the sample period, that gives us our absolute value for our settling time. And this is a 1% settling time. If somebody now says, I want a settling time of 3 seconds, and you have a sampling period, capital T, of 0.02, then you would use those numbers to find what n sub s, the number of samples in that particular interval of time, equals, and from that you can now find the radius in the z-plane. If somebody gives you r, then you can find how many samples it will take to eventually reach your 1% settling time. And that's using the ceiling function. That's performance spec number 1. Performance spec number 2, percent overshoot. Those are our hearts. And now if you're given percent overshoot, you can use this formula, or you could have that curve sketched that relates percent overshoot and zeta. But if you want, you can numerically compute zeta from this analytic form. And when are these really true? This is really just sort of rules of thumb. These are for second order systems. Pure two-pole systems, these zeta and percent overshoot values correlate via that formula. Or if you're given zeta, or if you're given the percent overshoot in terms of a zeta value, if somebody says, oh, I want a zeta value of 0.7, you know what that percent overshoot is, but you could compute it here, and you should find that it's 5% from this formula. That's the second performance specification. And the third one we talked about today, which are the angles or the wedges, and that's the peak time, where the peak time is pi over omega sub d. Omega sub d is the damped frequency of oscillation. Theta sub d, we went ahead and said we'll just define that to be omega sub dt. And now we can define our time to peak in terms of theta sub d as pi over omega sub d, but omega sub d is just theta sub d over t. And solving or putting that as a rational expression, we now have our peak time. T sub t is pi t over theta sub d. And now we can look at that two different ways. If somebody gives us the peak time, T sub p, either absolute or as number of samples, if they give it to us as number of samples, then we can essentially forget the capital T, or the sample period, and we have theta sub d as pi divided by n sub t. If they give it to us in absolute time, then we need to know the sample period, capital T, and we can then find or solve for n sub t. If somebody gives us the angle, theta sub d, we can just reshuffle that same relationship and find that the number of samples to reach the peak is pi over theta sub d. So if you had an angle, theta sub d, of 45 degrees, or that's now what, pi over 4? You now have pi divided by pi over 4, or the number of samples to peak is 4. So you reach your peak in 4 samples. All of these combined lead to the following table. Is this busy or what? Maybe not, but you can now, if somebody gives you settling time and percent overshoot, you know which row you're in. If somebody gives you settling time and time to peak, you know which row you're in. And you can use the appropriate expressions to derive or determine the pole locations, which are r at an angle of theta sub d, where r and theta sub d in the first row are given using just the known quantities r and zeta. In the second row, you're just using r and theta sub d. That's pretty straightforward. That's just r at an angle of theta sub d. And in the last row, you're using a zeta value, which are these hearts intersected with the lines, but you can get the radius using that last row in that table of relationships. This is just trying to summarize what we've done up to this point. Let's apply these to a particular problem. Suppose we now want to find a desired transfer function. So let's say that we now have the following example. Suppose we want to build or create a desired closed-loop transfer function, let's say capital T sub c of z, and plot the step response. For a system that has the following properties. Suppose it has a peak time of 10 samples and let's say a settling time of 30 samples. What shapes are you seeing in the z-plane relative to these two performance specifications? Peak time, what's the shape? What were we talking about earlier today? Wedge or angles. That's the peak time. And settling time, Oprah, circles, right? So now we have circles and angles, and we want to make that intersection, essentially. Let's now figure out what we have. We're given T sub P, and in this case, N sub P is what we were told. No one even gave us a sample period. We don't need it, but if we want to put some hard numbers to that or be thinking in terms of actual time, then we would need the sample period, and we could relate that to the actual time to peak little t sub p as n sub p, or 10 times the sample period capital T. We were also given the settling time in the form of the number of samples, where here the number of samples was 30. And again, if we wanted to put that into an actual value, we would then multiply n sub s, that 30, times the number or the value of our sample period. Not that we need to do that, but let's just pick something so that you're thinking about values. Let's just assume or suppose t was equal to 0.02 seconds, or 20 milliseconds. That's how fast we were sampling, just as an example. Then that would translate into a settling time t sub s of n sub s t, which is now 30 times 0.02, or we want to settle in a little bit more than half a second, or 600 milliseconds is what we want to settle. Or if we wanted to understand where we wanted to peak, or at what value of absolute time, that was now 10 of our sample periods, or this is now 200 milliseconds. That's just an assumption to give us something to think about. Now we want to settle with this system in a little bit more than half a second, and we want it to peak at about a third of that, in 0.2 seconds, in our step response of this second order system. What we want to do is, in order to build this T sub c from this information, we need to find the poles of this transfer function. We need to find poles of T sub c of z. Or that means we want z deltas at some r e to the j theta sub d. So if we can find an r, and if we can find a theta sub d, we have the denominator, at least, of our desired transfer function to achieve a settling time of 30 samples and a peak time of 10. Let's do the first one. Let's find r. For a 1% settling time, we know that r raised to the n sub s is equal to 0.01. we're trying to find r. We were given n sub s. We can do a translation or a reformulation of this expression by taking the log of both sides. And that log, let's say, is base 10, so that the 0.01 becomes minus 2. Or now we have n sub s times the log base 10 of r is equal to log of 0.01, which is minus 2. And if we now solve for log of r and take the anti-log, which is raise everything or use that in the exponent of 10, we now have r is equal to 10 to the minus 2 over n sub s. Or in our case, we have 10 raised to the minus 2, and n sub s we said was 30. This now says that we want a radius of 0.8577, which is 10 raised to the minus 115. If we want to find the angle, then we can use this time to peak, which was pi over omega sub d. But remember that theta sub d was this omega sub dt, which gives rise to omega sub d of equaling theta sub d over t. Or now our time to peak is pi over theta sub d over t, or pi t over theta sub d. But we were given that time to peak was 10 samples. Or this equation now says that 10t is equal to pi t over theta sub d. This is our time to peak. The t's cancel, and we can now solve that for theta sub d. Theta sub d is now pi over 10, or 0.1 pi, and we all know pi to who knows how many digits, 3.14159. Oh, he knows? Okay. So now we'll just multiply that by 0.1 and not get the right answer. Or, I don't usually think in radians, but I know what pi is in terms of degrees, so theta sub d is now 180 degrees divided by 10. So I now know my angle, theta sub d, is 18 degrees. I know the radius is 0.8577, and my angle is 18 degrees, so I now have this 0.8577 e to the j, let's say pi over 10, or this is now 0.8577 e to the j 18 degrees. And I can now say that z delta is 0.8577 cosine of 18, which is 0.8157 plus j, 0.857 times the sine of 18, which ends up being 0.265, where this is my r cosine of theta sub d, and this value is r sine of theta sub d. Now I know what my denominator looks like in this two-pole system that gives me a peak time of 10 samples and a settling time of 30. I now can say that T sub c of z is z, and I want my real part to be at 0.8157, and my imaginary part is at 0.265. What I don't know is what my numerator looks like. So let's make some assumptions. We know that it's going to be some gain k, or some scalar. Let's go ahead and just put a z there, and a z there will give me a 0 at the origin, and it will actually, I have a z over a z squared, which gives me just a 1 sample period delay between my input and the output, instead of a 2 sample period delay. So this particular factor, let's just say we have a 0 at the origin, and the 0 at the origin actually produces a pole 0 excess of 1. We have 2 poles and 1 0. And having a pole 0 excess of 1 says that we now have a 1 sample period delay between the input and the output. Now, how do I find k? Question. So where did the z at the origin come from? It came out of thin air. But I just said I want to have a 1 sample period delay, and now I'm just going to make that 0 fast. I'm going to locate it right at the origin. That's a fast 0. It's there because I wanted a 1 sample period delay, and I knew that I was going to get 2 delays if I just had a constant in the numerator. So now I have a 1 sample period delay. How do I find a value for k? What would I pick for k? What would be a convenient value for k? Pardon? 0? No, that wouldn't be a convenient value. If I picked k equal to 0, then I wouldn't have to do the problem, would I? Yeah, I would have 0 output from that transfer function, and that would basically say I'd kick the system, and what would happen? It would just be, it would sit there. It wouldn't have any kind of ringing. It wouldn't go to anything. We want it to, what? Jump over and back to where we're at, and where do we want to end up? If I hit it with a 2, where do we want it to go? Do we want it to go to 6? We want it to go to 1/2. If I said, I'm going to put in an input of 2, where would I like it to probably end up? 12? So if I put in a 2, where do I want it to go? What if I put in a 3? You guys aren't going to graduation if you keep answering this way. Oh, he's good. Okay. He's a graduate student. So I put in a 3. Where do I go? Probably I want to go to 3. If I put in a 2, I probably want to go to 2. If I put in a 1/2, I probably want to go to 1/2. What's going to make that happen? What would make that happen? What's that mean? If I say I put in a 5 and I want to go to 5. If I put in a 4, I want to go to 4. I have a unity gain. What kind of a gain is that? At what frequency is that gain a 1? Is that a gain of 1 at a frequency of 20? At DC, isn't it? Because I put in a constant, I want it to go to that constant. That's a DC gain. What does that tell me? Does that help me find k? And that k is not sitting in an office, room 456A. This is the letter k, right? K, yeah. Luckily, you don't have any rotten tomatoes to throw. But if we want a DC gain of k of 1, what's that translate into? What does that correspond to in terms of t sub c of z? If we want the DC gain of this to be 1, where do we evaluate this? DC in the analog setting is 0, isn't it? That's s equals 0. But remember, we're doing this mapping. Z is equal to e to the st. We plug in 0 for s, we get z equal to 1. So we want actually t sub c of 1 to equal 1, or we now have k, and we had a z upstairs at the origin. We had a z here, and this was 0.8157 squared plus 0.256 squared. Whoops. I interchanged I think that was 0.265 squared. The only unknown in that expression is now the k, and I can solve for that. K is now going to be 0.1042. Is that clear? We wanted a DC gain of 1. That forced the value of our transfer function, t sub c, at z equal to 1. I wanted to pick k so that the whole thing ends up being equal to 1. This now assures that. I now have my desired transfer function. It's got a k of 0.1042 z over z minus 0.8157 squared plus 0.265 squared. And you're going, yeah, really. So let's see if that's actually the case, if this is consistent. Let's look at MATLAB, and I'm hoping you can sort of see this. What was our numerator? Had a gain of 0.1042, and it had a z at the origin. How do I put a z at the origin in my numerator expression? Now I have to worry about putting in polynomials as the form of a row vector. And now I need a constant. I had z minus something, and that minus something was 0, wasn't it? It was z minus 0 in my numerator. So my constant is 0. My z coefficient is, so now I'm saying if I looked at this, if I wanted the numerator is now 0.1042 times 1 comma 0. That will give me a polynomial of z plus 0. And I'm scaling that by 0.1042. Here, then, I need to multiply that times this row vector of 1 comma 0. That's my numerator. What's my denominator? Well, my denominator was second order. It was z squared minus 2 times 0.8157. And then what was the constant? The constant's going to be 0.8157 squared plus 0.265 squared. I'm just going to do that. I'm going to have MATLAB do that for me. So here I have 0.8157. Oh, and I'll just be really rough. 0.8157 plus 0.265 times 0.265. Is that okay? There's my denominator. Oh, the question was, why did I use element-wise? I was actually just trying to use minus 2.0. So that should be just minus 2.0 times 0.8157. I wasn't trying to use element-wise. That's just dealing with a scalar. So element-wise, that's just multiplying two scalars. So hopefully I have a minus 2 times a 0.8157. I wasn't trying to say a point or a period multiplication symbol. And I think this minus 1.63 is okay. So the question was, why are you doing this element-wise multiplication? Well, luckily, I wasn't really doing that. I wasn't planning to. That was just trying to multiply two scalars. And I hit a period after the 2 for whatever reason. Let's now create the transfer function. Let's say that that's gz is equal to transfer function numerator times the denominator, but now it's assuming an analog system unless I tell it a sampling period. And do I know a sample period? 0.02 is what I said. Let's just suppose, but if I didn't know, if I didn't have a sample period, I could just tell MATLAB, you know what, I don't know what it is. I'm going to just say it's minus 0. And MATLAB's smart enough to know that, oh, you don't have a specified sample period. It's just unspecified if you put in the t of minus 1. And if I now said something like, let me go into a different figure. Let me say step of gz. This is now the response that I would obtain. But now MATLAB doesn't do a very good job of realizing that that's not in seconds, that's in sample periods. So when you see 10, that represents 10 sample periods, and that's when we're peaking. That's what we wanted. And then we go out here to 30 sample periods, and that's where we settle. That was our settling time. So this seems to be producing what we wanted. Now we could go back and say, suppose that I wanted to do that for a given sample period. Let's say that t was equal to 0.02. Let's just say that that's our sample period. Then we could say, oh, I want to define a transfer function with that particular sample period, and it will do it. And now it says, oh, your sample time is 0.02 seconds. Which, if we looked at this particular step response, we would now have this in units of actual seconds. Now the units make sense, and we should be peaking at 200 milliseconds, and we should be settling by 600 milliseconds. Question? Yes, so when you put in minus 1, it's essentially saying, oh, capital T is going to be like a 1. And yes, if you put in a 1, it's going to do things kind of weird for you, I'm afraid. So I would not put in a 1, I would put in a minus 1, and then it tells you that you are not specifying the sample period. If you put in a 1, then it's going to be, if you do anything else with that transfer function, it's going to be assuming that the sample period was 1. And that may not be what you want MATLAB to be thinking or using. Now, we've been talking about hearts and logarithmic spirals. You can actually have MATLAB produce some of these for you. You could just say, give me a z-grid. And it will give you, oh, this. And you're going, that does not look very heartsy to me. And why not? Well, maybe because the horizontal and vertical axis are not equal. So you can go back and you can force that. You can say axis equal. And now it looks a little bit better in terms of angles are angular or the right angle representation. Now, you may still argue that that's not a very attractive part. That's okay. But they're logarithmic spirals. And it's labeled. Now you can see where the 0.9 logarithmic spiral is and the 0.8. Or for zeta of 0.7, which would give you a percent overshoot of 5%, you now know where that lives on this particular line. If you wanted, you could say, well, I don't want all of that. That's too busy. So you might say, can I just have particular values of zeta? Maybe you say you want zeta equal to, let's just pick some, 0.3, 0.7, and 0.9, just for grins. Let's just say that that's what we want. And maybe we don't want those other lines. Those were natural frequency lines. They're perpendicular to these logarithmic spirals. And those are occurring at 0.1 pi over t, etc., based on what the natural frequency is for a given capital T. If we don't want those on there, let's just say w is equal to 0. And now we can say, give me a new figure, although this one, again, I want to make the horizontal and vertical the same spacing. And let's now do a z-grid with z and w as arguments. And now it's labeled the zeta values of 0.3, 0.7, and 0.9. And as we increase zeta, our heart shrinks. And maybe this isn't very clean, but we could actually put in, if we said, oh, let's let x equal -1 to 0.01 to 1. And let's say y is equal to 0 times x. And I want, basically what I'm doing now is I'm putting a horizontal line and a vertical line in that maybe ugly picture before. So I'm holding my figure window. And now what I want to do is plot x comma y. And now I have this horizontal line through the center so that I can sort of orient myself. And if I wanted to, I could also plot just the opposite, essentially, and say plot y comma x. And if I didn't like those colors, which I maybe shouldn't have done, maybe I should make those both black. I could make those black by doing something like the following. Suppose that I now go in here and say, make that line black. And black has a K in it, so the MATLAB uses K for the argument. Who knows what that's, but now I have a black horizontal line. I could do the same for the vertical line. And now I have these markings, and maybe you don't want this entire globe. You know it's symmetric. Maybe you want to use more of your paper for the top half, because you're really just interested maybe in the top half. We could actually do that. We could say, let's just restrict our axis and make it go from, let's say, -1 to 1 in the x coordinates, and y, let's go it from 0 to 1. And now we have this half of a unit circle, but this now maybe is cleaner to play with if we just want to put in one x and we know that its twin is down below. So now you have tools, and maybe I can post some of these z-grid things on the website for you to use if you're now trying to sketch or plot different z-plane pole locations that might have particular z values, or now you would just say, oh, a 0.6, you might have to get out your ruler and find 0.6 here and then measure that off and intersect that with your logarithmic spirals. Question? So the z-grid does not have anything to do with the transfer function. The z-grid just puts this grid on top of, if you had a pole zero diagram, if you said PZ map and plotted your poles and zeros, then you could say z-grid on top of that, and then you could see what the appropriate damping ratio, and maybe radius r for your particular poles and or zeros. But z-grid is independent of your pole location or zero or your transfer function in general. Let's now change gears a little bit and try to connect sample period with the Nyquist and aliasing. So that now we want to look at a sampling frequency and how that relates to the Nyquist frequency that you've probably heard about before, and what that might mean if somebody starts talking about aliasing. Or how are these three words connected or related? How do we relate our sampling frequency to the Nyquist frequency and to alias, this concept of alias, where alias is really a frequency looks like another frequency. It's aliasing it. That's the way that we're using alias. In terms of what we've been playing with, the S-plane to Z-plane mapping helps us sort of connect these ideas. And we've been using, to make this connection between the S-plane and the Z-plane, Z is equal to e to the st. But when we did that, that now is introducing our sample period. So when we make this mapping, we are now sort of imposing this sample period or sampling frequency on this mapping. This t introduces a sample period. What we want to understand is, what does this t actually do for us? What does t do for us? And in fact, what I want you to go home with today is that t actually, the sampling period, once you've picked that, that now restricts what kinds of frequencies you can actually see or resolve. T restricts the range of frequencies we can actually resolve or see. And the way that we'll try to make that clear is, let's try to remind ourselves what we've heard before about Nyquist. Suppose we have a Nyquist frequency, which I will now call omega sub n. Do you remember what that was equal to? Or do you remember a particular relationship between Nyquist and frequencies, maybe a sampling frequency? Something with a 2 in it, doesn't it? The Nyquist frequency has a 2 related to something. Well, the Nyquist frequency is actually half of the sampling frequency. So the sampling frequency, omega sub s, divided by 2, is our Nyquist frequency. This is now omega sub s over 2. And I like to think of omega sub n, it maybe is easier to think of that as being the folding frequency. And that might become clear in a minute. But pictorially, what we have is the following picture. If I plotted the magnitude of a signal's absolute value, its frequency response, and let me just give it a generic shape that's easy to draw. Let's say that it's now sort of this triangular shape, and let's say that the highest frequency I will just label as omega sub h, and now its mirror image is visible on the negative frequency side. So I now have omega sub h and minus omega sub h, and by sampling, I actually start making copies of this. So that now every omega sub s and minus omega sub s, I have a copy of what I just created. And that's due to the sampling of my continuous time waveform. Now, if this picture gets copied every every integer multiple of omega sub s, what do I know about the leftmost point of that first green triangle? What frequency is it at? If it's a copy of the blue that's centered at 0. So this one right here has what value? That should be omega sub s minus omega sub h, right? I've just shifted that blue over by omega sub s, and so now the leftmost side of that first green triangle is omega sub s minus omega sub h. This frequency would be omega sub s plus omega sub h. That h is for a highest frequency. But if I do not want these to overlap, what do I want to ensure? If I do not want these triangles overlapping, so I don't want frequencies from one bleeding into another frequency or another triangle, I need to make sure that this leftmost frequency of the green triangle is not down and touching the rightmost blue frequency. Or in terms of an algebraic relationship, what I'm saying is I want to make sure that omega sub s minus omega sub h remains larger than omega sub h. That's so that I do not have any overlap. And that means I'm not going to have any aliasing. Frequencies that are higher than omega sub h will remain outside of my vision, as long as this is true. But what does this impose? If I push that omega sub h to the other side, or I now can see that omega sub h needs to be less than omega sub s over 2. And that's where this Nyquist frequency comes in. The highest frequency that I can now resolve is bounded by the sampling frequency divided by 2. Omega sub s over 2 is the highest frequency that can be resolved in a sampled waveform. Frequencies higher than omega sub s over 2, if I actually had some, would actually appear to be between DC or 0 and that frequency, omega sub s over 2. And I'm not going to have time to go through all of that, I may do that after the fact, but now what would happen if I would have a frequency that's higher than omega sub s over 2? Then that's going to get folded over that Nyquist frequency, or the omega sub s over 2 location, and it will appear as if it was between DC and omega sub s over 2. And we'll have to pick up at that point, or I'll supply that information online after this lecture.